In this video, we will look at a Euclidean geometry question from one of the past papers. Okay, let's look at the question. In the diagram, DGFC is a cyclic quad. Okay, so we'll go ahead and highlight that cyclic quad. So it's DGFC. That's a cyclic quad. Okay, so next, AP is a tangent to the circle at B. So this line AP, that's a tangent of the circle, right? So if this line is a tangent to the circle, we will look for tangent-chord theorem, tangent perpendicular to radius, or tangents from the same point. Okay, so we will have angle B1. Angle B1, that's the angle between the tangent and the chord, is equal to which angle? Is equal to the angle that is subtended by this chord in the opposite segment. How do you get that angle? You go like this, you go like that, where the two lines meet, that's the angle subtended by the chord. So angle B1 is going to be angle D1. So that is the tangent-chord theorem. We're done with tangent. Okay. Then what else do we have? Chords DP and BC are drawn, and then DG produced. It means DG. DG is a straight line, and CF meet in E. DC is produced to A. Again, that one is a straight line. And we are also told that EA and GF are parallel to each other. So there's EA and there's GF that are parallel to each other, which means there we have alternating angles with F1 equal to F2. So let's highlight those angles that are alternating. So it's F1 is equal to E2. Okay. Now we can answer the questions. The very first question, give a reason, question 9.1. Give a reason why B1 is equal to D1. And we've already indicated that B1 equal to D1 because of tangent-chord theorem. So 9.1 is going to be, reason will be tangent-chord theorem. Okay. Then number 9.2, they want us to prove that ABC, so triangle ABC is similar to triangle ADB. Okay, let's highlight those triangles. Okay, so let's highlight triangle ABC and triangle ADB. So triangle ABC will be this triangle. Okay. Then the other triangle is triangle ADB. Okay, triangle ADB will be the red triangle. So that's ADB. So the blue, we're proving that the blue triangle is similar to red triangle. So you just have to prove that the two triangles are equiangular. Okay, first of all, angle A1 is a common angle, both in triangle ABC and ABD, the red triangle and the blue triangle. So angle A1 is equal to angle A1. So that is a common angle. Okay. What else do we have? Remember, we've already said that angle B1 is equal to angle D1. That is tangent-chord theorem. So we will indicate that angle B1 is equal to angle D1. So that is tangent-chord theorem. Okay. Then lastly, angle C in the blue triangle, angle C is equal to angle B. That will be the sum of angles in a triangle. So angle C is actually B, angle CA is equal to D, angle BA. So basically when I say B angle CA, I'm referring to that angle C. It's going to be equal to what? It's D angle BA equal to that. Those are the remaining angles. So that is sum of angles in a triangle. Then we can conclude and say, therefore, triangle ABC is similar to triangle ADB. That will be angle, angle, angle. Okay. Then the last question, now 9.3. 9.3, they say here, prove that angle E2, angle E2, which is, this is angle E2. They want us to prove that angle E2 equal to angle D2. Okay. And remember, we've said that this green shape is a cyclic chord. And in a cyclic chord, we know that the exterior angle equal to the opposite interior angle. Basically, we have a situation like this. So if this is a cyclic chord, and then that exterior angle must be equal to opposite interior angle. So that's the same thing here. Exterior angle, which is F1, must be equal to D2. But first of all, we know that E2 equal to F1. Angle E2 equal to angle F1. Remember we said that is alternating angles. Alternating because GF is parallel to EA. And then from there we're going to say angle F1 is equal to angle D2. Angle D2. That will be exterior angle of cyclic chord. Cyclic chord. Then we can now conclude and say, therefore, angle E2 is equal to angle angle D2 because they're equal to the same angle. Both of them are equal to F1. Then we have proved that.